All right. Hello, everyone, and welcome to the 14th session here at the IEP Workshop on data synthesis. So I think it's about 10:20, so we're probably ready to start the first presentation, and that will be by Laura Mitchell on using reproducibility and automation to generate the seasonal monitoring report. So if we could start the video on that, that would be great.
Welcome to Using Reproducibility and Automation to Generate the Seasonal Monitoring Report. My name is Lara, and I'm giving this presentation on behalf of the Seasonal Monitoring Report team, which includes Rosemary Hartman, Nick Rasmussen, David Bosworth, Sam Bashevkin, Michael Kufkin, Jason Dubois, and Louise Conrad. Ecological monitoring programs produce a lot of data, and those data are processed and packaged in various forms for managers and stakeholders, including summary reports, publications, presentations, and technical reports. A traditional workflow for these products involves copying and pasting results into a standalone document. But in some cases, a more practical approach is to use tools and workflows designed to make it easy to run, and hence reproduce, a complete analysis. This is the idea behind reproducible reporting, also known as dynamic reporting or literate programming. This is the process of interweaving code and narrative text to produce output that can be regenerated as needed when something changes. As a simple generic example, suppose we have a vector of temperatures and want to present the mean. Then a sentence in the reproducible report might look like this. The mean temperature is mean temperatures, degrees Celsius, where there is a mix of regular text and code to be executed. In the output, the code representing the calculation is replaced by the mean itself, and any time the data in the temperatures variable changes, the output will be updated as well. In this presentation, I'm going to describe how and why we incorporated elements of reproducibility and automation into one particular report called the Seasonal Monitoring Report. But as we're going through the slides, I invite you to imagine that we're talking about one of your technical documents and consider if and how some of these elements might improve your workflow. The IEP Seasonal Monitoring Report, formerly known as the Status and Trends Report, is a graphical report that was created to provide managers with an overview of seasonal trends associated with different environmental and biological parameters in the San Francisco Estuary. The report presents full time series for selected water quality, plankton, and fish surveys in the interior delta, Suisun Bay and Marsh, and San Pablo Bay. The Seasonal Monitoring Report is a synthesis project with collaborators from multiple agencies. It has changed format over time, but the current iteration is available online through the IEP's public engagement page, as well as the GitHub repository where it's hosted. Some of our goals for this synthesis effort, on the technical side of things, were to be able to incorporate new survey data as they became available as easily as possible. That means streamlining tasks such as updating figures and captions and ensuring that alt text is set. We also wanted to incorporate transparency and accommodate collaboration as tenets of good science and synthesis. In terms of content, we wanted to be able to make objective, quantitative statements about seasonal trends. And all of this together becomes synonymous with reproducibility, dynamic reporting, and to the extent possible, automation. The idea of reproducibility transcends any particular software or language, but we used R for the Seasonal Monitoring Report because it's common in ecological analyses, and there are a lot of easy-to-use and reliable R-based tools for accomplishing the goals I showed on the previous slide. The current version of the report is generated with the Bookdown package, which works in conjunction with some of the other foundational dynamic reporting packages like R Markdown, Pandoc, and KnitR. These provide a really simple and fun way to create a nicely formatted document in a variety of outputs, including HTML, Word, PDF, LaTeX, and EPUB. For the seasonal monitoring report, we're using an HTML formatted Bookdown report that looks like this, with a navigable table of contents on the left, main content pane on the right, and some formatting tools at the top. One advantage of the Bookdown package is that it produces nice looking, ready to go HTML by default. These tools are thoughtfully designed so the user can focus on the content of the report and decide for themselves how much customization of the HTML, CSS, or JavaScript they may want to do. Although the SMR project doesn't currently use these tools, I want to plug the suite of packages known as the Office First. They allow you to create highly customized and reproducible Word and PowerPoint documents. I've used them for other projects, and I highly recommend checking them out. One of the benefits of using reproducible reporting principles is having code for tasks that you know will need to be repeated. One of the first tasks is typically retrieving data. The Seasonal Monitoring Report pulls datasets from online repositories, including the Environmental Data Initiative, EDI, the Open Data Portal maintained by California Natural Resources Agency, Columbia Basin Research at the University of Washington School of Aquatic and Fishery Sciences, Bay Delta Live, and FTP servers. As a research community, we really appreciate when data managers make data available and programmatically accessible through repositories. Another area where reusable code comes in handy is in standardizing the appearance of elements like figures. As an example, the Seasonal Monitoring Report uses custom stat functions, extended from the ggplot2 package, that handle missing data and show long-term averages on time series figures throughout the report. Over the course of this project, Dave and Michael went above and beyond and created the S-Monitor package. This contains the functions for retrieving data from the repositories I mentioned previously, so they can be used in projects outside of the Seasonal Monitoring Report. It also contains the customized stats I described for standardizing figures. One other advantage of using the Bookdown format is that it is easy to standardize styles across separate projects. For example, we wanted to create some consistency between the Seasonal Monitoring Report and an online version of the Environmental Monitoring Report that is under construction. We did this by applying the same CSS, which is an easy way to achieve that consistency between documents. Another benefit of integrating data processing and writing is that you can incorporate tests to make sure everything is as expected. I don't know that the Seasonal Monitoring Report does a lot of this at the moment, but it's great and useful, so I decided to include it here. In terms of what this looks like, it's really up to the user, but it can be as simple as adding some if statements to stop execution of the code if, for example, the number of records in a data set is inaccurate, or if values fall outside of the expected range. As you might expect, there are tools that help with this. For example, the TestThat package provides a framework for incorporating more formal testing than simply inserting various if statements. It's also designed to automate the process so you can incorporate testing in your project without getting sidetracked. The documentation for TestThat has the following text. Testing your code can be painful and tedious, but it greatly increases the quality of your code. TestThat tries to make testing as fun as possible so that you get a visceral satisfaction from writing tests. Testing should be addictive, so you do it all the time. I think this accurately describes not only testing, but a lot of the concepts I've talked about here. It takes effort to make projects reproducible, but your future self will be happy that you made the effort. And the more practice one gets, the less time it takes. As I mentioned earlier, one of our goals was to reduce the amount of time spent updating text each time we added new data. One way we could do this was by programmatically generating figure captions, which make up a majority of the text in this primarily graphical report, as well as alt text that helps meet accessibility requirements. Captions give a simple quantitative statement about the value for the current report year in relation to the long-term average, or the long-term average itself if data for the current report year aren't available yet. The alt text gives a simple description of the figure, including the year range and value range. To do this, we're currently using functions that generate and invisibly store the caption text and alt text as part of a ggplot object at the time that it's created. The text can then be extracted as needed using the getCaption and getAltText functions for displaying the caption and setting the alt text of image tags. Although this aspect of the report is still under construction and will likely get updated, I was excited to get this first implementation up and running. Looking forward, some of our future goals for the seasonal monitoring report are to update it more frequently. In a meeting a while back, I remember someone saying, "Things that get updated more frequently get more views," and I like to keep that as a kind of mantra in the back of my mind. We're also considering including viability metrics like biomass and primary and secondary productivity, measures of uncertainty, and a summary of trends in community assemblages. As you start implementing some of these concepts, you may realize that there are a lot of levels to reproducibility, and I like to visualize this in terms of a tree. On the data side, the top level would be describing who collected the data and how you obtained it. And in my tree analogy, this approach would be like representing the tree with a leaf. To go a little further, you might provide your reader with a copy of the data itself, for example in CSV format if the data set is small enough. And in this case, we might say that the tree is represented by a branch. If you wanted to go a step further, you might reference a persistent data repository where the reader could access all the data and metadata, and that would be like adding a trunk to the tree. And then sometimes a repository will have different versions as the data get updated, so if you provide the version number for the data, then your reader can fully access and understand the data that you used, as well as find contact information for the dataset, and that might be considered getting to the root of the data. We could make a similar analogy for the code used to perform data analyses. In this case, providing a copy of the text files might be the top level. Making the code portable and easily runnable by another user, for example by using an RStudio project, would be the next level. Since code changes over time, you may want to consider using version control software on your own project and keeping track of the version numbers of the tools you used. Depending on the complexity of the analysis, you may also need to report the operating system used. How deep you go will ultimately depend on factors like the expected lifespan of the project, complexity of the analysis, and the resources available for maintenance, and it can get overwhelming. My best advice is to start simple, but start somewhere. What I have talked about today fits into the larger theme of reproducible research, which encompasses things like making data and code available through repositories, literate programming, version control, code reviews, and pair programming. A lot of research communities and journals are adopting these ideas, and synthesis projects provide a good opportunity to learn and apply best practices for reproducible research. I would like to thank field crew members who collect the data we used for this project, data managers for making data available, and the agencies that allow us to work on these kinds of collaborative projects. I also thank Sarah Perry and Gianfranco Saracino for their contributions to the project, as well as people who have taken time to provide input and feedback on how we can address management needs. This includes, but is not limited to, Brian Maharsha, Josh Israel, Brian Schreier, and Ted Flynn. And with that, I will take any questions.
Thanks, Laura. That was a really great talk. If anyone in the audience has questions, please submit them with the Q&A box or feel free to raise your hand. To start off, I guess, Laura, I was wondering if you could talk about the biggest challenges you see in the automation of this report.
That's a good question. Automating the captions it's just like the first draft is very simple, but we probably want to go back and think about maybe slightly more complex statements, but still quantitative statements that we can make in an automated fashion, which might take some more thought. So just making some of the statements a little bit more complex than they are now.
Yeah, definitely. So we have one comment from Barb Byrne who said, no question, but I feel inspired, which is great to hear. And then Nicole Kwan is asking, can you recommend any training resources for getting started on transitioning reports to these more automated formats?
Oh, that's a good question too. I don't have any in particular. If you just Google the format you're interested in, look down, a lot of good tutorials will come up. Like the authors of those packages and other RStudio employees put together a lot of really good resources. So yeah, I don't have any in particular, but they're really easy to come across while you're researching.
Yeah, I think there's a whole book on book down.
Yes, yeah. Yeah.
So that can be a good place. It's kind of a very extensive user manual.
Yeah, and you'll definitely come across it. It's probably the first result you find.
Yeah. Let's see. And then Rosie is asking, if someone has data or graphs that they would like to see added to the report, how can they get added?
You can reach out to us either directly through email or through GitHub.
Great. Any other questions from the audience? Feel free to put them in the box or raise your hand. We have a couple more minutes here. Oh, Rosie, go ahead.
Yeah, I just wanted to say in terms of other training resources, if you are not a member of the Bay Delta Data Science Project Work Team, contact me or Sam or Laura are also on the list. And we have quarterly meetings where we discuss all kinds of data science issues, including a lot of the ones that Laura brought up here. So it's a great resource for people who want to learn more.
Okay, here we go. A question from Kat Pien about how long does it take to update the report each year?
That it depends. If the repo that we're pulling the data from hasn't changed much, then it can be, a matter of minutes. But if something did change, something in the workflow changed, even as simple as field names, then it might take a little bit of debugging. The biggest holdup is usually just waiting for data to be available.
Yeah.
Yeah, but if you have a good workflow, then you can update it, just like I said, over the course of a couple minutes, which is really helpful so you can work on other things.
And then we had one comment from James White who said, I've had good luck making complex captions in Markdown with fig.cap tied with paste 0 commands.
Oh yeah, yeah, and doing some of that.
Yeah, great. Well, thank you so much, Laura. That was a really great talk. I think we are ready now for the next talk, which will be given by Tanya Rogers and Shruti Khanna, and it's on identifying drivers of food web dynamics through data integration and synthesis.
Hello, I'm Tanya Rogers from NOAA Fisheries, and I'm here with Shruti Khanna from the California Department of Fish and Wildlife, and we'll be presenting on identifying drivers of food web dynamics through data integration and synthesis. As you can see from the title slide, we're just two of many collaborators on this research. The projects we'll be presenting on today arose from a working group organized by the Delta Science Program and NCEAS, the National Center for Ecological Analysis and Synthesis. This was a training and synthesis workshop focused on Delta food webs, which had 18 participants from 9 different agencies and universities, where we collaborated on data integration and analysis with an emphasis on open science practices. So our working group split into 2 subgroups tackling different but related questions. I'll be presenting on the first project on identifying drivers of food web dynamics, and Shruti will be presenting on the second project about the effect of flood management on estuary health. The first project involved the 9 co-authors shown here. And this project was focused on the drivers of fish food supply on an estuary scale. The issue being that many fish species are declining in part due to declining food, but we have a limited understanding of the drivers of the aquatic food supply. So our research questions were first, what is the relative influence of abiotic drivers, bottom-up effects, including food supply, and bottom-up effects such as predation on different components of the delta food web, including phytoplankton, zooplankton, and fishes, and how do these effects vary among the different regions of the estuary and between annual and monthly timescales. To answer these questions, we compiled a range of different data from many different monitoring programs on nutrients, chlorophyll, flow, clams, zooplankton, and fishes. And we summarized these data for 4 different regions of the estuary, which were the north, south, west, and far west regions. And these were also summarized over 2 different timescales. So we had a data set of annual averages from 1980 to 2020, and a data set of monthly averages from 1995 to 2020. The analytical method we chose to use was structural equation modeling, or SEM, also known as path analysis. This method is very similar to multiple regression, but allows for multiple response variables that are linked together in a network, expressing some causal hypothesis about how those variables interact. Using this approach, we can model both direct and indirect effects, as well as residual covariance and latent variables. So our approach was first to develop a conceptual model of the delta food web as a group that was based on known trophic relationships. We then simplified the model to what was actually feasible to fit given the data we had, which involved using aggregates or different subsets of variables. We then fit the model and evaluated model fit, making modifications as necessary. And when that was completed, attempted to interpret our results. So this was the conceptual model that we developed, which was based on the group's collective knowledge of the system and also somewhat by data availability. So this expresses relationships between nutrients, phytoplankton, for which we use chlorophyll as a proxy, various zooplankton groups, clams, estuarine forage fishes, which were an aggregation of these 5 species here, their predators and competitors, and 3 abiotic drivers that we settled on, which were flow, temperature, and turbidity. So in terms of the model setup, we used scaled log abundance for most variables. We developed models at 3 levels of spatial and temporal organization. So annual, total, annual by region, and monthly by region, which were paired with the annual and monthly data sets we developed. Due to time constraints, I won't be discussing the annual model, but you can ask about it later. For the monthly model, we divided our analysis into 3 submodels, one using upper trophic level aggregates, one using lower trophic level aggregates, and one using individual zooplankton groups. Since many of the monthly variables were highly seasonal, we ended up removing seasonality by subtracting monthly means. So we're essentially modeling the relationship between seasonal anomalies. We also used 1 month time lags as predictors, which allowed us to simultaneously estimate bottom-up and top-down effects, as well as the effect of self-regulation or autocorrelation. Also, due to time constraints, I'll only be presenting on these 2 models. So this was our upper trophic level model, which had 3 response variables. So these are estuarine forage fishes, specifically the index from the Bay Study midwater trawl, which was sampled year-round. We have predatory zooplankton, which is the sum of mysids and predatory copepods. Herbivorous zooplankton, which is the sum of cladocerans, herbivorous copepods, and rotifers. So phytoplankton, represented by chlorophyll, was included as a bottom-up driver. Clams were included as a top-down driver, where the clam species used depended on region, since different species are found in different regions. Top-down effects on fish included syncharchids, marine fishes, and silversides, and these variables depended on region. So in this diagram, the different colored arrows represent different types of interactions that are represented by each path. So to make the results more digestible, I'm going to present each interaction type sequentially. So the numbers here are the R-squared values for each response variable. And as you can see, the model doesn't explain a majority of variation in any of these variables, so just keep that in mind. In the following figures, the blue arrows will represent positive effects, red arrows will be negative effects, and gray arrows are non-significant effects. So first, we found that most everything is a good predictor of itself the following month, which is not terribly surprising. For bottom-up effects, we do generally see positive effects of lower trophic levels on higher trophic levels, and these effects seem to be more prevalent in the north and south than the west and far west. In contrast, top-down effects tend to be more prevalent in the far west and west than in the north and south. We can also see that the Potamicorbula clam species has a negative effect on zooplankton, whereas the Corbicula clam species in the north and south does not, which is consistent with Potamicorbula being known to have a higher grazing rate. Also, the top-down effects of fish only appear to be present in the north, which could be related to recent expansion of submerged aquatic vegetation in this region. Effects of abiotic drivers were various, and I don't have time to discuss all of them, but I'll point out that in 3 of the 4 regions, higher turbidity was found to have a positive effect on fish. And this is what those results look like altogether. Now moving on to the lower trophic level model. This model also had 3 response variables, which were clams, chlorophyll, and nutrients, specifically dissolved inorganic nitrogen. And here the effect of phytoplankton on nutrients was not lagged because the lag wasn't supported by the data. This model also includes effects of higher trophic levels on subsequent nitrogen levels, which can be interpreted as nutrient cycling. So due to time, I'm not able to present the specific results for this model, but I will present a summary of results for this model and for the last model together. So if we're to look at the total effect size for each type of interaction, which are the rows here, for each of the 6 different response variables in each of the 4 regions, and color the ones that are statistically significant, we get this table here. So some summary points are that self-regulation is important to consider for many species on a monthly timescale. Also, the relevance of bottom-up and top-down effects varies by taxon and region. So for instance, for herbivorous zooplankton, top-down effects appear to be more prevalent in the outer estuary, but bottom-up effects more prevalent in the inner estuary. Also, we saw top-down effects of chlorophyll on nutrients, but less evidence for bottom-up effects of nutrients on chlorophyll. Also, abiotic drivers are important for many species, although the effect of any particular driver varies by region and taxon. Some other considerations, so there are many variables such as chlorophyll that had a lot of unexplained variation. Also, the data in some cases suggested paths that appeared to jump trophic levels. Also, some of the signs of the paths were not as we would have expected based on a priori knowledge. So there are several possible explanations for these results. So we could be missing variables or missing indirect effects. There could be interactions among predictors, so non-additive effects, or nonlinear effects, neither of which are accounted for in this modeling framework. Also note that while we found that bottom-up effects seem to be more important for fish than top-down effects, we lacked good data on large predators of fish, so that's something to bear in mind. Also, we ended up excluding many abiotic drivers due to collinearity, so differentiating among them and determining which drivers are most important remains a challenge. Nonetheless, our findings can suggest interactions that are supported by the existing integrated data, which could be used in development of other types of food web models. So now I'll turn it over to Shruti to present on the second project.
Thanks, Tanya. The aim of the second study is to determine the impact of floodplain inundation on estuarine health. In today's talk, we will focus on one estuarine function, primary productivity. This project has 9 collaborators from 7 different agencies. Ample research has illustrated the value of floodplain inundation to food production, which can lead to increased food export downstream, improve native fish survival, and hopefully reduce our reliance on hatcheries. The challenge today is that engineered landscapes, like our delta, have led to a loss of floodplain inundation frequency and connectivity. Loss of connectivity has in turn changed the historic food webs, reduced access to productive floodplain habitat, and has curbed the growth potential of native fish. This study uses 3 diverse lenses to examine the problem. We are conducting a meta-analysis of existing literature on the food production implications of floodplain connectivity. The results of this meta-analysis will inform our exploration of quantitative models and the predictors and response variables that we are focusing on. The results of the quantitative modeling will further inform a spatial modeling technique called circuitscape to explore how productivity moves through the landscape during flood inundation periods and dry periods. For the quantitative modeling, we are using 2 different approaches, the frequentist and the Bayesian approach. For a response variable, we have integrated measurements of chlorophyll A, and for our predictors, hydrologic connectivity metrics such as flow, inundation, tidal information, and primary productivity relevant data such as air and water temperature and solar radiation. These data are being collated from multiple sources and agencies such as USGS, CDEC, EMP, and YOLO bypass stations, and simulation products such as DAMAT. In early data exploration, we found that our response variable, chlorophyll A, was not normally distributed. However, by using a log transformation, we could get to a fairly normal distribution. Of the predictors we chose, flow from the day of observation and lag days were all highly correlated as expected. Temperature and solar radiation were also well correlated. We started with a very basic linear model and moved to other models as dictated by our data. To incorporate temporal autocorrelation observed in our response variable and our residuals, we moved to a generalized least squares model. But then, as we brought in and integrated more data sources, our chlorophyll A measurements were coming from multiple stations. To incorporate the random effect of station, we moved to a linear mixed model approach. About 10% of our data falls in periods of floodplain inundation, while the other 90% is during that period that the floodplain is not inundated. We think that our LME model is not effectively modeling the dry period. Hence, we intend to test the use of generalized additive mixed models so that the dry and wet periods can both be malleably fitted. Parallel to this frequentist approach, we have also been following a Bayesian approach so we can explore whether there are lags in the response of chlorophyll A to any of our predictor variables. In the next iteration of models, we plan on including water temperature and tidal information as predictors and also incorporating data from the YOLO bypass itself. This will be done by including a categorical variable for region, the floodplain, the region directly downstream from the floodplain, and the region bypassing the floodplain. We tried a couple of model selection approaches for our LME model. This table shows the forward selection method using the Bayesian Information Criterion, or BIC. Cutoff for adding a predictor was preset at 10. Ignore the third and fourth column for now and focus on the first 2. The forward selection process determined inundation days was the most important variable to include in the model out of inundation, flow, temperature, and solar radiation. In the second step, to determine if there was another predictor that could be added to the model, None of the other three predictors dropped the BIC by more than 10, hence none of them were included. The final model thus only included inundation days. We were surprised by this result and wondered if the LME model was not doing a good job modeling 90% of the data from the non-inundated periods. So we used the same model and the same model selection process, but just for the non-inundated period. Naturally, we had to exclude inundation days as a possible predictor. The results of this exploration are shown in the third and fourth column. The most important predictor in this case was flow. And again, as we tested for the second variable to be added, the process strongly rejected the addition of a second predictor. Thus, during floods, inundation period seems to be the most important predictor of productivity. However, for the rest of the time, flow is the strongest predictor. In either case, solar radiation or temperature are not selected as significant predictors. As mentioned, we are also conducting a Bayesian analysis and have used the deviance information criterion for model selection. The DIC is the adjusted within sample accuracy that penalizes increased complexity. Based on lower DIC scores indicating better performance, the model selection suggests that current day flow Q and a lagged version of flow extending back up to 21 days called Q-ant may provide similar information, as do temperature and solar radiation. One take-home message from this initial Bayesian model analysis, which is also supported by the frequentist modeling, is that inundation days may have important effects on chlorophyll response. However, the parameter estimate for inundation days compared to other covariates is quite low, and we may have to account for inundated and non-inundated periods separately in the model, as suggested earlier. I know we haven't shown you any visualization of the results, but bear with us while we continue our exploration of the data and modeling approaches with much more outreach in this coming year. Intended products for both of the working groups include data publications, the code used for analysis, journal articles, outreach materials for the public and for managers, presentations to a variety of audiences, and training materials from our workshop, which are posted at this website. We'd like to thank the DSP and NCs for facilitating this working group, as well as the instructors and organizers who assisted us along the way. Thanks everyone for listening, and we are happy to take questions.
Great, thank you, Tanya and Shruti. So if anyone has questions, please put them in the Q&A box or raise your hand so we can unmute you. To start off, we have a question from Rosie, which I think should be applicable to both the projects. So were there any food web components you thought might be important but did not have enough data to include in the model? Maybe Tanya, if you could answer first, then we could go to Shruti.
Definitely. So one thing I mentioned was the having data on large predators of the estuarine fish is something that we struggled to find. We ended up using an index that was of essentially juveniles of those species, which isn't perfect, but is the best we were able to do for the centarchid groups. Mostly because the adults are not sampled well in any of the data sources that we had for the time period that we were looking at on the time resolution that we were also looking at. So that's one thing. Another thing is that chlorophyll is a very coarse proxy for phytoplankton. So plankton don't eat chlorophyll, they eat particular types of phytoplankton. And there wasn't really much data on at a finer resolution for the phytoplankton group. So we ended up using this very coarse proxy, which did not have a very high R-squared value in any of our models. So there are, I think, more finely resolved phytoplankton data that's now being collected, but it wasn't collected for a long enough time period for us to use for this model.
I'll pretty much second what Tanya said later, is that we also wanted to look at phytoplankton data rather than just chlorophyll A as a proxy. But because you have to have enough of a time series to tease out these effects, we had to stick with chlorophyll A for now. And the other thing that we are hoping to look at is zooplankton data as a response variable, and that too is into the future. We are not quite sure if we'll have enough data.
Great. Well, thank you both. I think we're just at 11 now. So it's time to move on to the next talk, which will be given by Jereme Gaeta on predicting winter run Chinook salmon and salvage using a machine learning framework.
Hello, thanks for joining me. My name is Jereme Gaeta. I'm a senior environmental scientist with IEP and CDFW. And today I'm going to talk to you about a winter run Chinook salmon project I've been working on with Brian Maharja from USBR and Trinh Nguyen, also from IEP and CDFW. Winter run are listed as an endangered evolutionary significant unit, and that's largely because of disruptions to their life cycle. So prior to the modern era, as subadults grew into adults, they'd make their way from marine habitats into the San Francisco Estuary and through the Delta into the main stem of the Sacramento, where they would mature and move into tributaries to reproduce. Now, by midsummer, those eggs would start hatching, swim-up fry would emerge, and as the fish moved into fall, they would begin moving into the main stem of the Sacramento River and going back south, reversing their trail back to the ocean and marine habitats where they'd grow for a couple years and repeat this cycle. Now, this is not quite their current life cycle anymore, unfortunately, and that's largely due to a loss of connectivity to spawning tributaries. So that means that the adults now have to spawn primarily in the main stem Sacramento River, which likely has a pretty big impact on their reproduction, also on the development of those eggs into fry. To add a little bit more injury, very oftentimes they can get routed into the southern delta due to negative flow at Old and Middle River, routing them towards the salvage facilities and the water projects. In 2020, the incidental take permit for the state water project stated that a tool focused on predicting winter run Chinook salmon entrainment events at salvage facilities must be provided to the salmon monitoring team staff to use as part of their real-time risk assessment. In other words, we need a tool to help us understand when they're going to be showing up in salvage so we can adjust exports potentially or other management actions. So the overarching goal of the project that I'm going to talk about today is to minimize endangered winter run Chinook salmon entrainment risk, and we're measuring entrainment risk by detection and salvage, while continuing to provide water to the state of California. The specific question we're trying to test is, can we predict salvage before winter run Chinook salmon ever are detected at the water projects? The approach we're using is a machine learning framework. Specifically, we're using the XGB DART, or the Extreme Gradient Boosting Dropout Additive Regression Tree algorithm. And I think this meme sums it up pretty well. The procedures are rather complicated, and I'd be happy to talk to anybody outside of this talk. But for now, I think the bottom line is that this method allows for non-parametric, non-linear data, and because of its regression tree framework, it allows for very, very complex interactions. So, our question, can we predict before they show up at salvage? This kind of model that we're generating produces two kinds of products. The first one is a classification, and specifically what we're asking is, 1 week from today, do we predict that there will be no winter run Chinook salmon in salvage, or a classification of absence? A classification of low presence, which is greater than 0 but less than 4.29 expanded salvage per day, or high presence, which is greater than 4.29 expanded salvage today. So the model will spit out for every day in the future which one of these classifications they think is going to happen 1 week from today. But it also yields a probability between 0 and 1 for the likelihood of each one of those classifications. We started with hundreds of covariates, and through several model selection procedures, in addition discussions with stakeholders, reduced our feature list. Feature is machine learning speak for covariate. We ended up reducing this list to 12 variables that included day of year, which is very important because we're looking at seasonal data, a couple of estimates of how many fish or indices of how many winter run Chinook salmon are in the ecosystem, specifically the pass estimate at Red Bluff and wild catch in the city of Sacramento. We have numerous flow metrics. We have 2 water temperature metrics. Again, one in the Sacramento River near Sherwood Harbor or near Sacramento the city, and one at Red Bluff. We have 2 management levers, the delta cross-channel position and exports, and Secchi depth also at Sherwood Harbor fell out as important. Now, one of the things you'll note is that all of these variables, with the exception of day of year, has a lag of at least 7. And so that means we can leverage that framework and take data from today or available today to predict what's going to happen in 1 week from now. And that's what I'm going to talk about for the rest of the talk. Now, because this is a time series data set, we have to take into account the time series nature of the data as we model winter run Chinook salvage. So our data set goes from late 2004 to mid 2021. And what we did was we broke our model into 5 what we call time slices. For each time slice, we keep 80% of that data, represented here by blue, and we give that 80% to the algorithm. The algorithm then builds models using that 80%. We built a total of 30 models, and each one of those models starts at a different place in the data space and builds about 15,000 regression trees. We then take the 20% that we didn't give to the model never sees it, and we can use that to evaluate how well our model performed. So this plot is a representation of how confident we should be in our model, or a visualization of our model performance. So for this first section here, each of these box plots represent when the model predicted absence. The truth was that 97.8% of those observations were right. In fact, the model said it would not be at salvage, and that's what we saw for 98% of the time. The remaining 2, the truth was either low presence or high presence. We see basically the inverse for the predicted high presence classification. So it gets it right 97% of the time, which is, both of these are phenomenal. However, when we move to that low presence classification, the model does well. It gets it right 85% of the time, but that's not as high as these 97 and 98% classifications. So, can we use that other model output, the probability, to improve our confidence in this estimate? This plot is going to show that other type of product, the model predicted probability of low presence for every day. And when the model got it right, I'm going to give it a correct classification of 1. So 1 means it was right. And when the model got it wrong, and it predicted low presence, but in truth, they were either absent, shown here by purple, or high presence, shown by green. And what you see is that when the probability is greater than about 0.65, the model always gets it right. We can use these data to build a logistic regression to provide an additional layer of information to end users. Specifically, what this model says is if the model predicted classification of low presence is less than or equal to 0.465 probability, you've got about a 50-50 chance of the model being right. So you should use a lot of caution. However, if you're an end user and the model spits out a probability of 0.604, well, now you're about 90% correct classification. And if that probability of low presence is at 0.75 or greater, at this point you should be incredibly confident in the model output. So the takeaway for managers or end users, such as the salmon monitoring team, is that when this model spits out an absence classification, believe it. It's right 97.8% of the time. When it spits out a high presence classification, you should also believe that. That one's correct 97% of the time. However, when it spits out a classification of low presence, you should take a deeper look at the data. And here's an example of a table that's in one of our write-ups that we will be providing with this model. So end users can use this predicted classification to see what is the probability that the model is going to get it right. Remember, our goal is to provide a tool. And so what we're now doing is we're taking these models and we're converting them into an online user interface that goes out whenever you upload the app and scrapes the internet for all the most recently available data. And what it can then do is give you a prediction for 1 week in the future. As an example of this, I went back in time to 2018, today, several years ago, March 24th, 2018, which was part of the testing data set. And I took the values for each of our features for that day. All 30 of the models predicted a classification of high presence. When we look at the second type of model output, we see that the prediction or the probability of high presence is at about 70% for March 31st, 2018. Now, there's another kind of tool that this model can produce that I think, or my team and I think, can be really useful to end users. And that's what's called a SHAP plot. What these plots are going to show is the first plot is for the classification of absence, the second is for the classification of low presence, and the third is for the classification of high presence. And the x-axis here are the model index going from 1 to 30. Again, we ran 30 different models. And the y-axis is that SHAP value, where if the value is less than 1, that means that feature is telling the model, do not choose this classification. If the SHAP values are above 1, that means that feature is telling the model, hey, based on today's value, you should consider this classification. Or in other words, as my colleague Tren likes to say, this tells us how the model is thinking. So let's start with the most important variable overall in our model, temperature at Sacramento River near Sherwood Harbor. On March 24th, 2018, the value we would put in is 10.5 degrees Celsius, which is pretty cold. Given that it's cold, the model says that means we do not think they're going to be absent. That is not a good classification to make. We do, however, have a lot of weight towards low presence and a pretty decent amount of weight towards high presence. We can then move to the second most important feature, which is day of year. For this day of year, the model's saying it's unlikely that we're going to get an absence, and it is likely we're going to get a low presence or a high presence classification. We can then move on to the catch metrics, the wild catch near Sherwood Harbor and the pass estimate 6 months ago up at Red Bluff. And what's interesting is the catch near Sherwood 3 weeks ago is actually pushing towards a vote of absence or a classification of absence, where the pass estimate 6 months ago is pushing towards a classification of high presence. Now, I was curious about this, so if we go back and look at the data, this makes sense. We have a decent pass estimate 6 months ago, but we have nothing that we caught 3 weeks ago at Sherwood Harbor. We can then move forward a couple metrics and we can look at exports. And we see that the exports are saying it's very unlikely we're going to get an absent. And in fact, it is likely we're going to get a classification of high presence. We can then add on all of the flow metrics. And what we see is that overall, we have a lot of negative evidence to classification. We have positive and negative evidence or support for low presence and a lot of support for high presence. And so this explains what the model was thinking and how all 30 of these models got to a classification of high presence. So let's do the reality check. Because we're using past data, we can see whether the model got it right. Well, the expanded salvage count on March 30th, 2018 was in fact 17 winter run Chinook salmon for that day, which is a classification of high presence. So if we circle back to our research question, can we predict salvage before winter run Chinook salmon are detected at water projects? The answer is yes. A week out, this model is very successful at predicting what's going to happen at the pumps. With that, here's my contact information if anybody wants to reach out. I'd also definitely like to thank my co-authors, Brian and Trent. Couldn't have done this without them. And I'd really like to take a moment to thank our stakeholder subgroup that we meet with quarterly, and these folks have provided us a lot of invaluable information and insight. And with that, I'd gladly take any questions or comments anybody has. Thank you for your time.
Thanks, Jeremy, for that talk. Again, feel free to put any questions in the Q&A or raise your hand. We have one from Barb Byrne, said, great talk. How did you decide on the low versus high breakpoints?
Yeah, that's a really great question. When we first took this model, not this model, but a preliminary version of this model to our stakeholder subgroup, one of the first things they said was, this is great, but it's only presence absence, which is what our first model was. And so we said, okay, we can break this into 3 classifications. And we asked them what that threshold was, and nobody really had a good idea or good justification. So what we ended up doing was saying, okay, if we get rid of all the absence data, let's just take the median value for when fish are present. So low presence is essentially means fish are present and they're less than the median value, and high presence says fish are present and they're greater than the median value.
I actually had a question related to that. I was wondering what the advantage is of discretizing your response variable rather than predicting the actual number of salmon that might be there.
Yeah, so this is all strategy, political strategy, I should say. Maybe not political, that's probably not the right word, but because this is a forecasting model or a projection model, we do not want to give end users reckless confidence in what we're predicting. And so we, in conjunction with our stakeholder subgroup, decided that the best way to do that is to be a little bit coarse. The second reason we did it is because there's another winter run Chinook model that's built by ICF. And that model, once Chinook salmon starts showing up at the pumps or at the facilities, the model is incredibly accurate at predicting the actual count. And so we said, we don't want to reinvent the wheel, so we want to provide a different kind of tool. So the way we plan to present this to users is use our model until they start showing up. And then you could use our model, but definitely use the ICF model because that'll give you an actual number. Good question. Thank you.
Yeah, that makes sense. Now we have 2 questions from Dalton Hands. I think the first one might be similar, but the second one is a new question. So he says, why a machine learning / associative model rather than generative model?
Dalton, full transparency, I don't know what you mean by generative model. Do you know, Sam, or could you elaborate on that, Dalton?
I do not. Maybe Dalton, you could raise your hand and we can unmute you, or you could type a clarification in the chat. Meanwhile, we had a question from Barb Byrne who asked, or who said, would be interesting to see if there is correlation of the observed salvage with the SHAP score. Have you done that?
Yeah, so we haven't yet. The SHAP values are really interesting. A plot I didn't show you is that over time, the way the model thinks changes. So we had a meeting with Lenny Grimaldo a couple weeks back, and we were walking through the full SHAP plots, not for a single day, but for the entire, from 2001 or 2004 to 2021. And I was pointing at a couple points where in 2007, exports predicted one thing, and in 2008, they predicted a different thing. And what he mentioned was that that was a change in the way that exports were managed. And the model actually picked up that shift in the way exports were managed. And so the model started to change its prediction. So it's not necessarily a correlation as in a constant exports always do X or past estimate always do X. It's a very complex interaction where exports matter, for example, when it's a certain time of year and that it's a certain water temperature and your past estimate was a certain value. So pulling out one individual variable doesn't provide a really great true look at what this model is doing, which is why I'm hoping to provide all of the features at once or variables at once.
Great, thank you so much. I'd encourage you maybe to put your email in the chat for Dalton Hand so you could follow up with him. I think we're about out of time here, but thank you again.
Will do. Thank you so much, everybody. Have a great day.
So next up, we have a talk by Eva Bush on changes here, climate change in the San Francisco Estuary.
Hello everyone, my name is Eva Bush and I am giving this talk on behalf of the Climate Change Mast. It represents a lot of work by a lot of people, culminating in the technical report called Synthesis of Data and Studies Related to the Effect of Climate Change on the Ecosystems and Biota of the Upper San Francisco Estuary. The IEP Climate Change Project Work Team, under the leadership of Larry Brown and Bruce Herbold, set out to improve the current understanding of climate change in the estuary. This conceptual model and report are based on an extensive literature search and synthesis by the Climate Change Mast team. There are 17 authors for this report. Through this search, we identified current and potential future impacts to three main ecosystems of the San Francisco Estuary: open water, tidal marsh, and floodplain. Then, for each ecosystem, the status of abiotic factors and select species, native and non-native, was evaluated, as well as the potential impacts of climate change on the ecosystem and individual species. Climate change is mostly described as trends in air and water temperature or sea level, despite the impacts to animals, plants, and humans frequently occurring as discrete events. So we may say that temperature is trending upward, causing lower level continuous stress to biota, but it is the heat waves that kill trees and fish, and those heat waves contribute to the long-term trends. In this report, we tried to view climate change impacts in the Delta as both a series of events and as a long-term shift in the baseline conditions. The first ecosystem I will talk about is the open water. We define that as any subtidal aquatic environment in the estuary. Open water habitats will be the ecosystem most affected by drought events and warmer temperatures. A reduced snowpack would lead to decreased outflow in summer months, especially in droughts, and produce conditions that favor many invasive fish, invertebrates, and aquatic weeds. Harmful algal blooms are more common in warm water conditions with high residence times. These same conditions are detrimental to most, but not all, native fishes. Salinity regimen can be reset by intervening years of high outflow, but may not occur often enough to allow populations time to recover. A reduced snowpack and overall decline in water supply will increase salinity and may lead to reconfigurations of the delta, as with the proposed Franks Tract redesign, with the goal of permanently reducing salinity intrusion. More variability in saline conditions may favor some of the native fishes and aquatic vegetation over their invasive counterparts. Tidal marshes are a very small fraction of the delta now compared to historically. With ongoing active restoration and future passive transformation by levee failure in places of suitable elevation, they are expected to become more abundant. Marshes may provide thermal refugia for cold water migrants by providing shade and evapotranspiration by vegetation, nighttime flooding of the marsh plain, and delta breezes cooling the air, as well as bringing cooler water on site. Though we don't yet understand why, marshes appear to be resistant to invasion by clams and some of the other invasive species in the estuary. This makes it possible for the high productivity of marshes to offset some of the productivity lost to invasive clams feeding in open water habitats. There is some uncertainty about sediment dynamics under climate change, but the most recent modeling indicates there will be an increased amount of sediment available in the estuary, as larger floods may mobilize larger amounts of sediment in the watershed. Additional sediment loads into the estuary would be welcome to counter sea level rise, after sediment loads sharply declined at the turn of the last century. How much sediment arrives in marshes will determine whether they can maintain their elevations or become open water habitat. The average salinity in marshes will increase as the sea level rises, which will change the plants that grow there and animals that use it as habitat. Due to the upstream location of floodplains, they are buffered from some climate change effects. Sea level rise, salinity intrusion, and storm surges don't have as large impact as they do on the open water and marsh ecosystems. Since the floodplain inundation happens in the winter when it's cooler, warming is expected to have fewer negative effects on floodplains than on other ecosystems. The larger floods we expect and have seen recently will produce more floodplain benefits. More flooding will slow drainage and increase residence time. If flooding occurs together with warmer temperatures, floodplains may be more productive with greater benefits to species spawning and foraging on the floodplains. On the other hand, the narrowing of the hydrograph may shift the timing of flooding and thereby reducing benefits to migratory species that may not arrive at the shifted time of flooding. Intervening periods of drought may reduce groundwater levels, affecting growth and survival of aquatic and riparian vegetation in the floodplains, and have detrimental effects on the species spawning and feeding there. Our estuary is already a highly variable place, becoming more so as climate change continues. In the last year, we experienced the longest dry season dry spell, ending in October with the wettest day and month on record, followed by the longest wet season dry spell on record, beginning January 1st. Sea level rise and losses of the Greenland and Antarctic ice sheets are tracking the higher end of model estimates. In the bay and delta, sea level rise will bring increased inundation area and higher salinity. The resulting increased area of saltier water will directly affect biodiversity in the marsh and wetland habitats, now supporting freshwater species as they become increasingly brackish. The increased inundation will also lead to increased predator exposure for terrestrial wildlife, such as salt marsh harvest mouse, while aquatic species may have less exposure to avian predators. Sea level rise will also require increases in delta outflow to maintain in-delta water quality for human uses. Climate projections of increased temperatures are more certain than those for precipitation in California and the Delta. Relative temperature impacts are projected to be greatest in areas of moderate to high elevation, impacting the size of the snowpack and creating earlier seasonal snowmelt, changing the hydrograph for water coming into the delta. Nighttime heat wave events have intensified in California and Nevada region, especially since 2000. And the latest heat waves brought extreme daytime temperatures as well, since the greater increase in nighttime temperature results in a decreased daily temperature range. Water temperature in the upper San Francisco Estuary is largely driven by the air temperature and the temperature of the inflow. The expected warmer atmospheric rivers, the shift in snowpack size, water content, and timing, as well as earlier snowmelt, would therefore warm the temperature in the upper San Francisco Estuary. Precipitation will shift. By mid-century, peak runoff may occur a month earlier than historical conditions. Earlier snowmelt and a greater rainfall to snow ratio will shift approximately 2.1 million acre-feet of runoff to earlier in the year. That is nearly twice the total volume of Folsom Reservoir. The shift in peak runoff is projected to be especially pronounced in rain-dominated watersheds, with runoff peaking earlier and higher. In snow-dominated watersheds, relatively little change in seasonality or peak runoff is expected until closer to the year 2100. These simulations also indicate a compression of precipitation, with more falling in the core winter months. A delay in the onset of the rainy season is already being observed and appears consistent with a predicted shorter rainy season in California. The shift in winds in the estuary is also uncertain. A study looking at recent decades, 1995 through 2005, found declines in delta breezes. Declines varied spatially and temporally across the delta, North Delta, and Suisun Bay. The authors made no connection to climate change, as the factors associated with these declines are unknown. But they did note that these declines are an important factor in driving water temperature and turbidity. At odds with the recent unexplained declines in delta breezes, a downscaled global climate model gives predictions of delta breeze events occurring with an increase in frequency and intensity. This predicted increase in delta breezes may help explain why the Bay Area and Sacramento Valley are anticipated to have smaller future change in heat wave events and extreme events than the rest of California in their model. Sediment supply outcome is still uncertain, but seems to lean toward an increase in supply. Earlier studies predicted a minimal effect or possibly a decrease of sediment supply with climate change, but more recent research points to an increased sediment mobilization from expanded wildfire burns and more atmospheric rivers mobilizing more sediment. We have general trajectories of the delta ecosystem, but key uncertainties remain and are mostly linked to a lack of data or synthesis of data already collected. Different aspects of climate change will drive change in the three ecosystems, and they will respond at different timescales. Open water habitats change greatly in temperature, flow, and salinity on short timescales, especially with droughts and heat waves, and will experience these rapid changes more frequently. The pelagic species are buffered to some extent from the effect of short-term changes due to their mobility, while sessile benthic species like clams must endure them. The open water habitat will continue to provide a salinity gradient, though shifting inland. This will affect some, but not all species, expanding habitat for some while shrinking it for others. The littoral areas, or edge of the open water, will continue to undergo large fluxes in salinity with the daily tides, extending the salt water further inland as sea level rises. Marshes will change gradually, depending on sediment dynamics and what effect increased atmospheric rivers will have, both the frequency and the strength of them, and the rate of sea level rise. Salinity and water depth changes brought on by sea level rise will affect the vegetation type of the marshes, turning some freshwater marshes into brackish ones. A more systematic temperature monitoring scheme in the tidal marsh channels can provide a better understanding of their importance as thermal refugia for cold water species. Monitoring of sediment dynamics during varying flood event levels would help identify sustainable marsh sites for restoration. Floodplains are an episodic ecosystem affected mostly by extreme flood events and severe droughts, but isolated from other climate change impacts. Management actions to help with impacts such as annular bypass, reconfiguring weirs to improve fish access to the floodplain, modifying agricultural return flows to assist movement of food into the river, and facilitating groundwater recharge may help. Temperature for off-channel habitats has been collected, and an important next step will be to incorporate data from these off-channel habitats into local and regional modeling frameworks. Monitoring of groundwater pumping and quantification of groundwater depth thresholds may be critical for preserving future biodiversity in floodplains. This was a brief summary of the technical report, but there are other publications from the Climate Change Project Work Team either already out or pending, where you can read about some issues in more detail. Thank you for the opportunity to present, and I will see if there are any questions.
Great. Well, thank you so much. If anyone has questions, again, please put them in the Q&A or feel free to raise your hand. Eva wasn't able to make it today, but Rosie Hartman will be here to answer any questions that might show up. So I had one question to start out. I was wondering whether you think that an estuary or watershed-wide lens might be helpful in better understanding or managing climate change impacts.
Well, a watershed-wide lens is always probably the most effective way to tackle any problem of an estuary. However, we kept it to just the estuary just because the watershed is so large, and even if we identify management tools we can use, implementing them on the watershed-wide scale can often be so logistically difficult. We thought we'd start small and start raising awareness of some of the issues, make the adaptations on the local scale when we can, and participate in some other California-wide efforts to look at a larger scale. I mean, we should be looking at the worldwide scale, really.
You can always scale it up, or you can always think about scaling it up. Yeah. It's difficult to implement. Let's see, another question I had, I think Eva went into this a little bit, but I was wondering, when we hear about climate change impacts, it's easy just to get pessimistic and think the world is dying. So I was wondering if you had thoughts on what we can do with the information produced by this report and this effort. How can we use our better understanding of climate change impacts on delta ecology to protect the environment and preserve native species and water supply?
Yeah, I think some of the big things kind of align pretty well with tackling some of the estuary's other major problems. Focusing on restoration of the habitat we have left, particularly off-channel habitat like floodplains, restoring marshes with sea level rise accommodation space, and adapting our managed floodplains to flood more frequently or at lower water levels, like the YOLO Big Notch project. And just starting to be aware of what impacts we're likely to see so we can start tracking it. And, any conservation story, there's no necessarily right or wrong, there's just what we think we want. And so starting to think about what things we want to manage to maintain and what things we might have to let go in terms of, it might be that certain species are not going to do well in the Delta, and we should just start managing for other species that fill similar ecological niches but have a different temperature regime, things like that. Some of those hard decisions to start kind of working through them.
So we have a question from D. Ellis. With more floodplain flooding in mind, how does pesticide use on those areas get dealt with? Is it investigated first?
Well, contaminants are one of the big kind of not smoking guns, elephants in the room. That's the overused metaphor. There's been a lot of investigation on that, and there's been a lot of uncertainty in terms of how big of a problem they are, what the effects are, how they really integrate with the ecosystem as a whole. We are talking about, more flooding or keeping the amount of flooding where it is now instead of having it go down. So it's not like we're introducing something new. And having the floodplain flood more often versus letting all pesticides accumulate for years and then have a flood, I don't know which would be better, but it's definitely something to be investigated. and to keep in mind as we're managing. Also, temperature will change the toxicity of certain pesticides. So as temperatures rise, the effects of those contaminants might change. We're also probably likely to get a new suite of pesticides coming in every 5 or 10 years. So yeah, definitely a lot of room for added study there.
Yep, there always is. Well, thanks a lot for answering the questions.
Well, our last speaker for the day, and I'm going to go ahead and jump in and introduce him because it's less awkward than having him introduce himself, is Sam Bashevkin, your excellent synthesis moderator here. And he is going to be presenting on water temperature inflow relationships in the upper San Francisco Estuary. So take it away.
Hello, everyone. I'm Sam Bashevkin from the Delta Science Program, and I'm here to talk about water temperature inflow relationships in the upper San Francisco Estuary. So as we are all probably aware, water temperature and inflow are both key variables in the estuary. Temperature is important for metabolism, predation, thermal stress, development rates, reproductive timing, and it's changing currently from climate change. Inflow, on the other hand, can determine salinity levels, is involved in water supply, floods, droughts, and has been altered seasonally due to infrastructure. But these two variables are actually related through a very complex causal web. So you can see that we have drivers including climate change, weather, snowmelt, water management, in-delta precipitation, delta air temperatures, upstream river temperatures that are all in this web connecting inflow to delta water temperature. So how are they actually related to one another? There's been some prior study on this. Some studies have found that reservoir-released inflow has little influence on delta water temperatures. Other studies have found that negative temperature inflow correlations can be detected in some regions and seasons. You'll notice, first of all, that these two statements aren't actually in contrast with one another. The first statement is referring specifically to reservoir-released inflow, where the second is just correlations between temperature and inflow. However, there's still a lot of room to understand what the overall relationship is between these two variables throughout the whole season, all of the seasons in the estuary, as well as throughout the whole region of the delta. So we decided to leverage monitoring data to resolve this question. Our main questions are on the slide here. So first of all, we asked how are water temperature and inflow related in the upper estuary? Then we asked how does this differ seasonally, spatially, along the salinity gradient, and including long-term temperature trends? And lastly, to what extent could in-delta precipitation be driving the observed patterns? So our approach was to integrate water quality data from long-term discrete monitoring surveys. We then developed spatially explicit models of water temperature inflow relationships, and we evaluated the spatial and seasonal differences in water temperature inflow relationships from those models. Our integrated data set had about 60,000 temperature records from 1969 to present, from over 400 unique locations and 9 different monitoring surveys. You can see the monitoring surveys pictured on the slide now. They include the Environmental Monitoring Program, Summer Townet, Fall Midwater Trawl, Delta Juvenile Fish Monitoring Program, Spring Kodiak Trawl 20 millimeter Survey, Sassoon Marsh Fish Study, Bay Study, and the USGS San Francisco Bay Cruises. We also included flow data from the Dayflow model of delta hydrology produced by the Department of Water Resources. And from this model, we took the inflow values as well as the precipitation. The model that we used was a generalized additive model known as a GAM, fit with the package MGCV for the statistical programming language R. In this model, we included surface water temperatures as our response variable. And there are a few predictor components here that I'll walk through. So we had a background spatio-seasonal smoother, which was a smooth of latitude, longitude, and Julian day. Generalized additive models are used to model nonlinear trends. So these smooths are nonlinear interactions among these variables. The second component was the temperature inflow relationship, which was also a smooth of latitude, longitude, and Julian day, but this time multiplied by the 30-day lagged mean inflow. By this, I mean for each temperature record, we looked at the prior 30 days and averaged the inflow over those 30 days prior. Lastly, we had a time of day correction, which was just a smooth of the time. We used a scaled T model family for heavily tailed data, which these were, and an AR1 process for the temporal autocorrelation. The focus of the study was on the temperature inflow relationship surrounded by the yellow box here. We extracted this model term, which you can think of as a slope smoothed over geography and season. We then plotted it to evaluate the temperature inflow relationship. We found that there was a predominantly negative temperature inflow relationship. So on the graph here, you can see that there are 12 subplots, one for each month, January through December. Each plot is a map of the study region, and the colors represent the temperature inflow relationship, which is the temperature change per change in total inflow. And as I said before, we detected negative temperature inflow relationships most commonly. In this type of relationship, higher inflow is associated with cooler water. And you can see those areas surrounded by a yellow box now. Positive temperature inflow relationships were also detected. These were found during the winter and downstream areas in the summer. And in this case, you have higher inflow being related to warmer water. So then we wanted to know whether incorporating the long-term temperature trend in the model might change the result. So water temperatures have changed over time. They've been steadily increasing. And there has been seasonal changes in inflow as well. And we want to make sure that these long-term trends weren't confounding the temperature inflow, or sorry, the temperature inflow relationship that we're detecting. So we fit the same model as before, but with the addition of the component in the orange box here, where now we had another component for the long-term temperature trend, which was a smooth slope by geography and seasonality, just as the temperature inflow relationship was, this time multiplied by the water year. And hopefully, if you remember the results in the prior slide, you'll realize that this is basically the exact same outcome. So you get the exact same result in terms of the temperature inflow relationship, whether the long-term temperature trend is incorporated in the model or not. Then we fit a model that substitutes salinity for geography, so we could examine this temperature inflow relationship along the salinity continuum. On this plot here, it looks a little bit different. Now we have salinity on the x-axis. We still have 12 subplots, one for each month. The vertical red dotted line represents the average salinity at the confluence for the month in question. So this should help you orient yourself geographically to the salinity continuum. The y-axis is now the temperature change per change in total inflow, or the temperature inflow relationship. What you can notice is that in February through July, there's actually an abrupt change at a salinity of about 1.5, where initially the temperature inflow relationship is getting larger with as salinity increases, but then at a salinity of 1.5, it starts decreasing as salinity increases, which is an interesting pattern. Also, the temperature inflow relationship is often lower at lower salinities, and lower salinities would correspond to the areas where the rivers are inputting into the delta. So what if we look just at in-delta precipitation? For this, we fit the exact same model as our first model, but we used precipitation instead of inflow. So this plot is the same as the first plot, except the color scale now represents the temperature change per change in precipitation instead of per change in inflow. We got similar results, but you can see the result is actually muted in the summer and fall. And this is expected because this is the season when precipitation is negligible. So you wouldn't expect there to be much of an association with precipitation when precipitation is rare. So I'm going to walk through some potential explanations for the results, starting with the dry season and then moving into the wet season. In the dry season, we found reduced or non-existent temperature precipitation relationships compared to the wet season. The temperature inflow relationship was thus much stronger than the temperature precipitation relationship. And this could imply external influences like river temperature or flow may be driving the observed temperature inflow relationship. This is further bolstered by the stronger temperature inflow relationship near the areas of river inputs, as we saw in this Lindy model, and you can also see it in the first model we presented if you look closely at the maps. However, this leaves open a question whether this pattern is because inflowing waters are cooler in this season or because of decreased residence time with higher flows driving the observed temperature patterns. In the wet season, we found consistent temperature inflow and temperature precipitation relationships. This could suggest that precipitation or its correlates could be driving the temperature inflow relationship. A positive temperature inflow relationship in the winter could be a result of warmer air temperatures accompanying atmospheric rivers. But temperature inflow relationships switched to negative in March at the end of the wet season, which was an interesting pattern. And we're not sure if it's due to cloud cover maybe having more of an impact in March when the days are longer and the solar intensity is stronger, or it could be a signal of snowmelt. So there's definitely a lot more to dig into here. So first off, I think it's important to note that the study looked at correlation but not causation. So we did not evaluate the impact of dam releases on water temperature, and you cannot use our study results to evaluate any impacts of dam releases on water temperature. This study shows that increased precipitation variability may impact delta water temperatures, since we found a relationship between inflow and temperature, as well as between precipitation and temperature. And water temperatures could be a hidden stressor during droughts. The magnitude of temperature change that we detected could alter the delta smelt spawning window or reduce juvenile salmon rearing time. Water temperatures could also be a contributing mechanism to the flow abundance relationships that have been detected for a number of species, such as longfin smelt. These relationships have been documented, but many lack a clear mechanism. It could be that multiple mechanisms underlie these flow abundance relationships, and these correlations that we found may help explain some of this relationship. For example, longfin smelt prefer cooler waters in general, and higher temperature during droughts may be one of the reasons why they do better in wet years. So I've mentioned a lot of areas for future work in the end of this presentation, but I'm just going to summarize them here because there are a lot of areas that we really need to dig into to understand why these patterns are appearing. One question is, what are the relative temperature differences among inflowing river waters and delta waters? I think this is a key question to figure out whether the influx of cooler water could be driving any of the patterns that we found. If that's detected, then it would be interesting to know whether cold water reservoir releases impact delta water temperatures. This has been investigated before by the Daniels and Danner paper I cited earlier. However, they only looked as far downstream as Knight's Landing. But they still detected a very minimal impact of the temperature of water released from Keswick Dam on water temperatures in Knights Landing. However, that Sacramento River is a really long distance from the dam to the delta, and there's a number of tributaries that are much closer, and they could have an impact. So we need further study to figure out whether the temperature of water released from those closer tributaries may actually influence water temperatures in the delta. And lastly, it'll be interesting to know whether atmospheric influences are really the primary drivers here, which is very possible. There's a lot of talk about hot droughts. And if air temperatures are warmer in general during droughts, that could be a huge component of why we're observing these patterns with no relationship, actually no causal relationship to the waters flowing into the delta. So lastly, I would like to thank Larry Brown, first of all, who inspired the study and was instrumental in kicking it off and determining the early methods for what we were doing. And of course, the monitoring survey staff, without whom we would have no data to analyze. Thank you.
Thanks, Sam. That was really cool. Any questions from the audience for Sam? Start things off. I'll start with one. So there's a high of 85 in Sacramento today. Sure all of you are well aware of the major heat wave going through this week. Any thoughts on the relationship we're likely to see between temperature and outflow this year?
Well, that's a good question. And actually, what is it? It's March. So that is one of the months when we detected a negative temperature and flow relationship. So, but it's hard to, like I said, we didn't assess any causal relationship. So that's one of the areas that I think is ripe for investigation is air temperatures and atmospheric influences, because like I said at the very end, that could very well be a primary driver here. And in that case, if it really is just air temperatures that are driving separately the inflow and the water temperatures in the delta, then that would imply that releasing water from a dam would have no effect on cooling the delta.
We have a question from Dalton Hance. Sam, have you looked at predicting temperatures from predicted flows, say from the River Forecast Center?
No, we have not used this model in the predictive capacity. I would guess if you wanted to predict water temperatures, you'd probably be better served basing it off atmospheric influences. I think it's well recognized that they are the primary driver generally in temperatures. While we did detect a relationship with inflow, that's not to say that temperatures are driven primarily by inflow.
Makes sense. Now I have a question from Peggy Lehman. How did the Sacramento and San Joaquin differ in the relationship between flow and water temperature?
That's a really great question. So we did actually detect stronger temperature inflow relationships along the Sacramento corridor than along the San Joaquin corridor in many of the months. That's one of the reasons why we think there may be a role of flow itself in driving these relationships, since the Sacramento corridor has much, much more flow than the San Joaquin corridor.
Cool. A question from Mike Dodrill. The latitude and longitude smooths are continuous in space, yet water temperatures in the delta are not, so land. Why not apply a smoother like a soap film smoother that reflects the land-water boundary?
Yeah, that's a great question. That's something we did look into, and ultimately we decided to not use a soap film smoother because water temperatures are driven primarily by atmospheric influences. So we felt that narrow boundaries between close by water bodies would not be a significant source of error in this model. Also, we did in a different study led by Brian Maharja, which is in review now, looking at differences between bottom and surface temperatures. In that study, we did use a soap film smoother, but we were only able to fit the outline of the study region within as a boundary for that soap film smoother. So we're not able to resolve any of the internal islands or internal land masses that separate water within the delta, which I think would be very important if we really wanted to use a soap film approach. But yeah, that is a great question.
All right, I think that brings us to the end of our session. Thank you, Sam, and I will thank all of the presenters and the audience. I think this has been a really interesting talk and a really great discussion.